Okay, chemists, welcome back. In this second half of Lesson 12.5, we are going to look at mechanism problems. There's 4 pretty advanced mechanisms for you to try today, and I'll walk us through the first 2, and I will leave you to do the other 2. Starting with the first one, we've got a unique reaction that takes an alkene and actually turns it into an amide with acetonitrile and acid. This is the molecule acetonitrile. It's a nitrile with just a methyl attached, similar to the number of carbons in acetic acid, so you can see the root. And we are in acidic conditions, so things I'm thinking of are what we've been seeing for weeks. Only positive charges. Likely the first step involves something gets protonated, and the last step, something is deprotonated. So let's start with that. Let's draw our cyclohexene and think about what could get protonated. Luckily, there's only one thing that can pick up a proton. It's the alkene. So we will have a new H on one of the carbons. Think about which carbon gets the H and which carbon gets the plus charge. Aha, Markovnikov's rule. We will get the more substituted carbocation. Then from there, I need to make a new carbon-nitrogen bond. Well, I've got acetonitrile, which looks like that if you draw it out. And when you see it, you're reminded that there's a lone pair on the nitrogen. So we can form a bond with the nitrogen. Carbon-nitrogen bond gets formed. That'll give me a new carbon-nitrogen bond, and a lot of stuff is along for the ride. Draw everything the same and only change what's changed. Now from here, I'll check back at the product. Okay, we've made our carbon-nitrogen bond. We actually have our other 2 carbons already there. I need to incorporate oxygen. Well, we have hydronium in the beginning, which we took an H plus away from, so we're swimming in water in all likelihood. So there's a water molecule around. And the water is nucleophilic at the oxygen. That can attack the carbon of this nitrilium ion and send a pi bond up to that nitrogen, getting rid of the plus charge. Remember, when you're doing mechanisms, it's always good practice to look at the curved arrows, draw the next intermediate without just copying mine. You should be able to use your curved arrows to tell you what the next intermediate looks like. So we now have a double bond to that carbon. Our methyl is still down there. There's a new carbon-oxygen bond, still with 2 hydrogens on the oxygen and a plus charge on that oxygen. Now, how do I get from this and turn it into the amide? All I gotta do is shuffle some protons around. It's not gonna happen all at once, but I clearly need to get those on top of the nitrogen and then lose one completely. So that's an acid-base reaction. That's an H plus transfer, which is fast and reversible, but we'll show the one that gets us somewhere. The nitrogen picks up an H, the oxygen loses an H. Like all H plus transfers, it's likely that it happens intermolecularly, but we'll just show it intramolecularly to save some time. Now our plus charge as a result is on the nitrogen. So how do I get from here to the product? We can actually draw a significant resonance contributor. I need to get the carbon-nitrogen bond to be single, the carbon-oxygen bond to be double. That's just a resonance contributor. There's a lone pair on the oxygen that can donate and send that pi bond up to the nitrogen. And all that does is give you a resonance contributor, but it looks a heck of a lot more like the product. You still got an extra H on that oxygen. Don't forget about it. So there's a plus charge there, and we are one step away from the end. Our first step was to add an H plus. Our last step will be to take that H away. I'll use another water molecule to do that. Break the OH bond, and that gets us to our product. 6-membered ring, methyl, nitrogen, H on the nitrogen, and the rest of the amide. Okay, so a mechanism that we have not seen before, but we can figure out because we're given the products and the conditions of the reaction. Let's try another one. This next one is a very bizarre looking functional group. We've got what looks sort of like an ester and another ester. There's also the appearance of a ketal. I feel like this has some ketal chemistry related to it. It's going to turn into a lactone and a carboxylic acid and an equivalent of acetone. If you forgot what acetone looks like, go ahead and draw it out to see where it is. That's your simplest ketone. In fact, as soon as I do that, I feel like I know where it came from. Acetone, a simple ketone, must have come from this ketal, and the rest of these carbons became this branched large molecule here. We are just in water, so it's neutral, which means we could have net neutral charges, both positive and negative. Hard part to figure out here is what new bonds are we forming? The first step is the hardest to realize, and it's this strained cyclopropane ring. The first step is actually attack of the cyclopropane ring. When you have a cyclopropane alpha to a carbonyl, it's actually quite electrophilic. It's reminiscent of conjugate addition acceptors. It's almost like doing a conjugate addition. Because of the strain of the ring, things can attack the beta position, and then similar to Michael additions where you send that negative charge to the alpha carbon, we can do something similar to a cyclopropane ring, and it just breaks open the ring. And that's actually our first step. So draw an arrow from the oxygen in the water to one of those carbons on the cyclopropane ring. That will break the carbon-carbon bond next to the alpha position, and you get a stable anion right next to the two carbonyls. So let's keep track of what that looks like. We're drawing everything the same and just keeping what's changed. So I still have my two esters. I still have those three other carbons down there. I still have the carbons of the cyclopropane, but this bond is gone. We no longer have that bond right there. Instead, there's a new bond to an oxygen that used to be part of a water. And it's got a plus charge on it. There's also a negative on the carbon that's right in between those carbonyls. In fact, that's why this happens. This negative charge, alpha, right next to the two carbonyls, is stabilized through resonance delocalization into both of those carbonyls. So it's not out of the question that that can happen. This opens up the six-membered ring, and it actually sets us up pretty close to how we can make a new five-membered ring. So what happens next? We're actually going to do a proton transfer and protonate that negative charge. It will take one of the H's. Again, probably happening pretty quickly intermolecularly, but I will show it intra. Now I have a neutral intermediate. And here I got to pause. Even though it was hard enough just to figure out those first few steps, I got to pause and figure out how this turns into all the remaining stuff. Well, we need to make a five-membered ring somehow. And if I look at this and I try to figure out how a five-membered ring can come out, start counting at one of the carbonyls and see if we can make a five-membered ring. 1, 2, 3, 4, and 5. There's the appearance of what could be a five-membered ring with an oxygen and a carbonyl. We have an alcohol and essentially an ester, and those can combine to make a different ester. This is a transesterification. So draw an arrow from the OH to the carbonyl carbon, send the pi bond up. We still have our six-membered ring. That's still open. But now I have a new five-membered ring as well. And here's the beginnings of the five-membered lactone that I see in the product up above. We still have to break open this six-membered ring so we can bring that O negative back down and kick out this other oxygen. That will give us a negative charge on the oxygen down there. We have the beginnings of our ketone. Sorry, of our lactone. We still have an extra H and a positive charge on this oxygen. So now that I'm here, I can really start to see where this molecule comes from. I just have to break this carbon-oxygen bond. And here's the point where we're going to pick up what we know about acetal chemistry. This is sort of like a different version of getting rid of your acetal. That negative charge that we just made can come down and form a carbonyl and kick out this oxygen. And if I just draw what my curved arrows show me, we've actually now separated the two molecules into the acetone. We just made it. There it is. So that's one of the products we're trying to explain. And then the other product has our 5-membered ring. Still with this H on it. I haven't done anything about that yet, so just keeping track of it. It's possible it could go away sooner from some solvent molecule. But now I actually have a zwitterion of the product. I just need to do an H transfer, and I can do it intramolecularly. Take that H off there and put it on the acid on the left, and you get your other product with a carboxylic acid and a lactone. So this is the product up above, just drawn upside down. So that's a challenging mechanism, I think. I hope you'll agree. The remainders are not quite as bad. I'd still like you to try them and then check your solutions. And we will see more of these mechanisms as we go on. Okay.